matter what.
Oh, really?
That's right.
Wow, I missed
That's,
it.
man,
That's what happens if you come in late.
Yeah,
Congratulations, Wesley.
I know, I'm
It's
happy.
a huge honor.
It is.
This would have been
Everybody.
early chapter 20, if you're looking for a place.
I equals delta Q divided by T.
Or,
Oh, yeah, because it's like,
now at this point, I'm about to screw up a minus sign, so let me just,
because it's not actually delta T, it's not like the change in time, it's like how much, or, no, sorry, it's not actually delta Q, it's like how much charge has flown by, right?
right,
Okay.
right. And I want to make sure I don't mess up the minus sign. All right, I think it's already been taken into account. All right. So I have this Q here, so if I multiply both sides by C, I get epsilon C times the cosine of omega t is equal to Q. So my current would be the change in epsilon C cosine of omega t over change in time. Epsilon again is the EMF, that's my maximum voltage that's coming out of the power supply. Capital C there is the capacitance of this capacitor I have in it. They're just constants. And I pull them out, I get epsilon C times the change in cosine omega t over change in t. Hey, we've done that before. What a coincidence. Still not convinced yet I haven't screwed up the minus sign. We'll run with it. Let's assume my notes are correct. What's the change in cosine omega t over the change in t?
Do the T's cancel out?
Nope. Apparently a huge impact was made earlier today.
Sign in the answer?
Say it again?
Is sign in what you're looking for?
Okay, there's a sign in what I'm looking for.
Okay. Does that have to do with the omega? Like this big thing that you were talking about?
Yeah, we did talk about it earlier, and it does involve omega. We're talking the slope of my cosine graph.
Right.
Cosine versus time.
So we're gonna end up with the negative omega sine of omega t.
So if I plotted that, because for my voltage for across the capacitor is just a cosine curve. My current is a negative sine curve. So if I plotted my voltage, it's a cosine. Done horribly. Better. My current is a negative sine. Again, going back to this negative sign here. Okay, no, we're still there. All right, and this is my current. So my phasors are they're not in phase anymore. Those two graphs are not peaking at the same time, they're not troughing at the same time. So if I drew, I will do a different phasor diagram. So at time is equal to 0, my voltage is at its peak. So if that's my voltage of my capacitor across the capacitor. My current is at 0 and then becomes negative. That's the way the phasors need to be in order to match this, because as time progresses, this becomes less positive to 0. That's this black line right here. I sub c starts out at 0 and becomes negative, because again, the value is the projection onto the horizontal axis. And then they still move it around at some angular velocity of omega. So we have, as we think about the phasors for capacitor, the current leads the voltage. I guess like pi over 2 radians, or 90 degrees. That is a right angle there. All right, here's the memory trick, because when we do inductors, inductors are going to be the other way.
What is the in front of pi over 2?
Pi.
Pi.
That's the word pi. Any other questions on reading my handwriting before I give you a memory trick? This is a memory trick that a student gave me. When you're talking about the EMF, it should regularly be an epsilon. However, before modern computers, to put an epsilon in there was a nuisance, and so a capital E worked. And so oftentimes, especially in electrical engineering textbooks is where I've seen it the most, they'll use capital E for the voltage. Instead of, because it comes from the EMF, which they couldn't bother putting an epsilon in. For a capacitor, current comes first. Ice. With inductors, the symbol is the capital L. As we'll find out, I guess on Friday, the voltage comes before the current. And I had it written on the board over there the last time, we didn't get to it, but Eli the Iceman is the memory trick to help you remember which one comes first. Now, at this point, it's a little bit abstract, I understand. We'll get into an actual application at some point. I was going to do inductors next and then actually do a problem.
Now, what does EY stand for again?
So the middle letter tells you what the component is. So capacitor and inductor. And then E stands for the voltage, I stands for the current. And so the voltage, for an inductor, voltage leads the current by 90 degrees. And for a capacitor, current leads the voltage. And I think the word to describe you at this moment is enthralled.
Like planning out when to go to the tutoring center for the rest of the week.
I'll note the first alarm went off. There we go, there's the second one. So unfortunately, clock says it's time to go. and let the Doors tune run through your head.
This was off topic, but I saw a video, I guess, last night of it was like a slow motion of a guy, putting a lasso around a bull. And, like, you see the, like, tension and friction in the rope in slow motion. And it was crazy, but all I could think about, I don't know if this will make you happy. To me, I felt like it ruined me. Was, oh my God, a physics problem about this would be a bitch.
If you send me that video, I'll subject some other group to it.
I need to find it. I was like, I don't know. That's how I like think about things now. I'm like, man, we could figure out the tension in that rope.
Yeah, my friends will ask me to find like the acceleration of things as if like I could find out. Like when we'll be at track meets and they'll be like, find that acceleration. Like how? Please tell me how.
I do want to make one comment. I'm going to turn this off first.